Welcome to the Digital Timing Interactive tutorial. We will discuss some digital timing errors and analysis tools such as the eye diagram. We will first introduce digital signals. We will then move to talk about jitter and drift timing errors. And lastly, we will discuss the use of the eye diagram for analysis. Digital signals. A logic level provides information about the bits carried. As an example, 0 volt may represent a logic 0 while 5 volts represents a logic 1 or vice versa. However, timing and logic level are both required to carry digital information from one device to another. This is done by referencing the digital waveform to a clock signal. A basic clock signal is a square wave with a fixed period labeled TP here. The period is measured from one edge of the clock, which is usually the rising edge, to the next similar edge. The frequency of the clock can be calculated by the inverse of the clock period, that is 1 over TP. Digital transmitters drive new data samples on each assertion edge of the clock, also called active clock edge. For some devices, the rising edge of the clock is considered the active edge. For others, it is the falling edge. Some newer devices even use both the rising and the falling edge of the clock. When a receiver samples the data on the digital lines, there are two timing parameters that must be carefully understood in order for the receiver to latch the data reliably. The data line must remain stable during sampling time. The first of these parameters is called setup time, or TSU. The setup time refers to the delay during which the data signals must remain stable before the active edge of the clock. The second parameter is called hold time, abbreviated TH. Hold time is the amount of time that the data signal must be stable after the assertion edge of the clock. If the setup times and hold time of a receiver are not met, the data will not be sampled reliably. Since we have now introduced the topic of digital signals, let's talk about some timing errors. The first one, jitter, is a deviation from ideal timing of an event, and is typically measured from the zero crossing of a digital signal. Jitter typically comes from crosstalk, simultaneous switching output, and other interference signals. Since jitter varies over time, measurement and quantification of jitter can range from a visual estimate on a scope to a statistics-based measurement. Clock drift occurs when the transmitter's clock is slightly different from that of the receiver. After many clock cycles, the difference between the two periods becomes noticeable and may cause loss of synchronization and other errors. On the example shown here, the difference between the two clock signals is very noticeable after only 3 clock cycles. These errors are very easily measured using visual tools such as the eye diagram. An eye diagram generally shows 3 periods of time demarked here by the vertical lines. These are 3 periods of the main system clock TP. An eye diagram is constructed by looking at the output of a digital transmitters over these 3 time periods. You can imagine that if the transmitter output 3 logical 0 values over the time periods, the plot might look like this. If the transmitter produces 3 logical 1s and we overlay this output on the same plot, it might look like this. Now if we overlay the transmission of a 0, 1, 1 in pink, a 1, 1, 0 in red, a 0, 0, 1 in blue, and finally a 1, 0, 0 again in green, notice that these are all the possible combinations of zeros and ones for the 3 time slices. Laying all of them on top of each other explains why this type of plot is called eye diagram. In real systems, jitter causes the edges of the clock signal to not all be exactly TP apart from each other. Each clock period varies by a small amount caused by small imperfections. Once you overlay millions of digital transmission on top of each other on the eye diagram, the jitter becomes to appear as you see on the slide. Additionally, All voltage levels are not perfect in real signals, so an eye diagram will also display the variance in voltage levels. All this noise causes the white area in the center of the eye to get smaller. The width of the white space in the final eye diagram is called simply enough the eye width. If your eye diagram is composed of enough samples, that is millions and millions of 3-time period transitions, the eye width is a good measure of the amount of time in any given time period that the data lines are stable. This can give you a good idea of how much setup time and hold time you could have. The height of the white space is called, again, no magic here, the eye height. If your eye diagram is composed of enough samples, that is millions and millions of 3-time period transitions, the eye height can tell you where your receivers VIH and VIL, those are high threshold and low threshold respectively, needs to be to sample the data correctly. The better quality your digital signal transmission, the more open white space you should see in the eye. To complete the explanation, let's look at a real eye diagram. The diagram on the figure was obtained using the National Instruments PXI 6562 100 MHz digital waveform generator and analyzer. In a real eye diagram, the plot is an intensity of the overlay transition. That is to say, the color of the plot is a measure of the percentage of overlay transition for any given pixel. The red areas show a relatively low percentage of the overlaid transitions. The white areas indicate a very high percentage of the transitions. Let's represent the assertion edge of the receiver's clock by the vertical solid blue lines, and the receiver's required setup and hold time by the dashed vertical blue lines. Let us also represent the receiver's VIH and VIL by the horizontal solid green lines. At the leftmost point in the eye, the red star indicates where the overlaid data transitions cross the VIH of the receiver. Notice that the line indicating the required setup time crosses through the star. This is the earliest time that the clock will occur to guarantee reliable data sampling. If the clock were to occur any earlier, the data line could still be changing during the required setup time period. Using a little animation, we can demonstrate the entire window in which the receiver's clock can be asserted and still correctly sample the data. The latest valid time is dictated by the receiver's hold time requirement. Here the star indicates the point at which the overlay transitions cross through the VIH point. This intersection marks the valid point for the clock assertion time plus the clock hold time. For this eye diagram, if the receivers VIH and VIL could be moved closer together, there will be a higher percentage of the clock periods where it is valid to sample the data. As you can see, the eye diagram is a great tool for understanding the effect of both voltage and timing noise of real-world digital systems. Congratulations, you have successfully completed the Digital Timing Errors and Analysis interactive tutorial. More information on this topic and other DMM related material can be found at www.ni.com. This site contains white papers discussing the NI 4070's architecture, DMM throughput, and benchmarks. Also included on the site are tutorials and a variety of example programs written in LabVIEW and other programming languages. For technical support, sales information, and other DMM related resources, please click on the links below. Thank you and good luck with your project.